To determine the minimum wire size for 277 volts lighting load, we need to follow a few steps. Let's assume we have a 2-inch riser containing 19 current carrying conductors including the neutral, 1 equipment grounding conductor, and 4 spare conductors. The longest run is approximately 200 feet, and all circuits are single pole 20 amps at 277 volts, with circuit breakers rated at 75 degrees Celsius. Our goal is to find the minimum THHN wire size required. Step 1 involves calculating the ampacity of the conductors. According to the National Electrical Code, specifically NEC Table 310.15, B16, the ampacity of a THHN copper conductor in a 2-inch conduit is 52 amps. This table provides ampacity values for various conductor sizes and insulation types under specific conditions. Step 2 requires us to calculate the total circuit amps. Since each single-pole circuit is rated at 20 amps and we have 19 circuits, we multiply 19 by 20 amps, resulting in a total of 380 amps. This represents the total current demand of all the lighting circuits combined. Step 3 involves determining the required conductor size. This is based on the smaller of two values, the ampacity of the conductors and the total circuit amps. In this case, the ampacity of the conductors from NEC Table 310.15, B16 is 52 amps, while the total circuit amps is 380 amps. Therefore, the required conductor size must be able to handle at least 52 amps. Now, let's refer back to NEC Table 310.15, B16 to find the appropriate THHN wire size that has an ampacity of at least 52 amps. Looking at the table, we find that a number 1 American wire gauge or AWG THHN conductor has an ampacity of 55 amps at 75 degrees Celsius. Since 55 amps is greater than our required 52 amps, this wire size is suitable. Therefore, the minimum wire size required is 1 AWG THHN. It is important to note that the spare conductors are not included in the ampacity calculation because they are not actively carrying current. However, they do contribute to the conduit fill, which must be considered when sizing the conduit. The neutral conductor is included in the count of current carrying conductors, as it carries the unbalanced current from the lighting circuits. Additionally, the 75 degrees Celsius rating of the circuit breakers is not directly relevant for this wire size calculation, as we are using the 75 degrees Celsius ampacity rating from NEC Table 310.15. B16 for the THHN conductor. To summarize, we calculated the ampacity of the conductors using NEC Table 310.15. B16. We determined the total circuit amps by multiplying the number of circuits by the ampacity of each circuit. Finally, we selected the minimum wire size based on the smaller of these two values, ensuring that the conductor ampacity is sufficient to handle the total circuit load. In this case, the minimum wire size required is 1 AWG THHN. When performing electrical calculations, it is essential to consult the latest edition of the National Electrical Code and any applicable local codes or regulations. These codes provide the requirements and guidelines for safe and compliant electrical installations. Always ensure that you are using the correct tables and factors for the specific conditions of your installation, such as conductor type, insulation, ambient temperature, and conduit fill. If you are unsure about any aspect of electrical calculations or installations, it is best to consult with a qualified electrician or electrical engineer. They can provide expert guidance and ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. Furthermore, it is important to understand the concept of ampacity derating. Ampacity derating is the process of reducing the allowable ampacity of a conductor based on certain conditions, such as the number of current carrying conductors in a raceway, the ambient temperature, or the presence of other heat generating equipment. The NEC provides specific derating factors that must be applied in these situations. In our example, we have 19 current carrying conductors and a 2-inch conduit. According to NEC Table 310.15, B3, A. When there are more than 3 current-carrying conductors in a raceway, the ampacity of the conductors must be derivated. For 19 conductors, the derivating factor is 0.45. This means that the allowable ampacity of the 1 AWG THHN conductor, which is 55 amps, must be multiplied by 0.45, resulting in a derivated ampacity of 24.75 amps. However, this derivating factor only applies if all 19 conductors are carrying current continuously. In our case, since the load is a lighting load, it is unlikely that all the circuits will be operating at their full rated current simultaneously. Therefore, we may be able to apply a demand factor to the load calculation, which would reduce the total current demand and potentially eliminate the need for derivating. A demand factor is a ratio of the maximum demand of a system or part of a system to the total connected load of the system or part of the system under consideration. The NEC provides demand factors for various types of loads, including lighting, in Article 220. The specific demand factor that can be applied will depend on the type of lighting and the expected usage patterns. If we can apply a demand factor that reduces the total current demand to less than the derivated ampacity of the 1 AWG THHN conductor, then we can use the 1 AWG conductor without further increasing the wire size. However, if the total current demand is still greater than the derivated ampacity, then we will need to increase the wire size to a larger size that has a higher ampacity. For example, a number 1/0 American wire gauge, or AUG, THHN conductor has an ampacity of 150 amps at 75 degrees Celsius. After applying the derivating factor of 0.45, the derivated ampacity is 67.5 amps, which is still greater than our required 52 amps. Therefore, if the demand factor does not reduce the total current demand sufficiently, we would need to use a 1/0 AWG THHN conductor. In addition to ampacity derivating, it is also important to consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for feeders and 5% for branch circuits. To calculate voltage drop, we need to know the length of the conductor, the current flowing through the conductor, and the resistance of the conductor. The resistance of the conductor can be obtained from NEC Chapter 9, Table 8. The voltage drop can then be calculated using Ohm's law, which states that voltage drop is equal to the current multiplied by the resistance. If the calculated voltage drop exceeds the recommended limits, we will need to increase the wire size to a larger size that has a lower resistance. This will reduce the voltage drop and ensure that the equipment operates properly. In our example, the longest run is 200 feet. Let's assume that the current flowing through the 1 AWG THHN conductor is 20 amps. According to NEC Chapter 9, Table 8, the resistance of a 1 AWG THHN copper conductor is 0.124 ohms per 1000 feet. Therefore, the resistance of 200 feet of 1 AWG THHN copper conductor is 0.248 ohms. The voltage drop can then be calculated as follows: voltage drop equals current multiplied by resistance, which equals 20 amps multiplied by 0.248 ohms, which equals 0.496 volts. The percentage voltage drop can be calculated as follows: percentage voltage drop equals voltage drop divided by source voltage multiplied by 100, which equals 0.496 volts divided by 277 volts multiplied by 100, which equals 0.179%. Since the calculated voltage drop of 0.179% is less than the recommended limit of 5% for branch circuits, the 1 AWG THHN conductor is acceptable from a voltage drop perspective. However, if the voltage drop had exceeded the recommended limit, we would have needed to increase the wire size to a larger size that has a lower resistance. In summary, to determine the minimum wire size for a 277 volts lighting load, we need to consider ampacity derivating and voltage drop. We start by calculating the ampacity of the conductors using NEC Table 310.15. B16. Then we determine the total circuit amps by multiplying the number of circuits by the ampacity of each circuit. Next, we apply any necessary directing factors based on the number of current carrying conductors in the raceway and the ambient temperature. We then calculate the voltage drop to ensure that it does not exceed the recommended limits. Finally, we select the minimum wire size based on the most stringent of these requirements. It is important to consult the latest edition of the National Electrical Code and any applicable local codes or regulations to ensure that your electrical installation is safe, reliable, and compliant with all applicable codes and standards. Always consult with a qualified electrician or electrical engineer if you're unsure about any aspect of electrical calculations or installations. One additional consideration is the type of overcurrent protection device being used. The 75 degrees Celsius rating of the circuit breakers is relevant in ensuring that the terminals of the breaker are rated for the temperature that the conductor can reach under full load conditions. While we use the 75 degrees Celsius column in NEC table 310.15. B16 for determining the ampacity of the conductor, it is essential to verify that the breaker terminals are also rated for 75 degrees Celsius. This ensures that the connection between the conductor and the breaker remains safe and reliable under normal operating conditions and potential overload situations. If the breaker terminals are only rated for 60 degrees Celsius, then the ampacity of the conductor must be based on the 60 degrees Celsius column in NEC table 310.15. B16, which would likely require a larger wire size. Therefore, it is always important to check the temperature rating of the overcurrent protection device terminals and ensure that it is compatible with the conductor ampacity being used. Another important factor to consider is the conduit fill. The NEC specifies the maximum allowable percentage of the cross-sectional area of a conduit that can be occupied by conductors. This is to ensure that there is sufficient space for heat dissipation and to prevent damage to the conductors during installation and operation. The allowable conduit fill percentage depends on the number of conductors in the conduit and the type of conduit being used. For example, for 3 or more conductors in a conduit, the maximum allowable fill percentage is 40%. To calculate the conduit fill, you need to know the cross-sectional area of each conductor and the cross-sectional area of the conduit. The cross-sectional area of the conductors can be obtained from NEC Chapter 9, Table 5. The cross-sectional area of the conduit can be obtained from NEC Chapter 9, Table 4. The conduit fill is then calculated by summing the cross-sectional areas of all the conductors in the conduit and dividing by the cross-sectional area of the conduit. If the calculated conduit fill exceeds the maximum allowable percentage, you will need to increase the size of the conduit to provide more space for the conductors. In our example, we have 19 current carrying conductors, 1 equipment grounding conductor, and 4 spare conductors for a total of 24 conductors. Let's assume that we are using rigid metal conduit, or RMC. According to NEC Chapter 9, Table 5, the cross-sectional area of a 1 AWG THHN copper conductor is 0.1330 square inches. Therefore, the total cross-sectional area of the 24 conductors is 24 multiplied by 0.1330 square inches, which equals 3.192 square inches. According to NEC Chapter 9, Table 4, the cross-sectional area of a 2-inch RMC conduit is 3.356 square inches. The conduit fill is then calculated as follows: conduit fill equals total conductor area divided by conduit area multiplied by 100, which equals 3.192 square inches divided by 3.356 square inches multiplied by 100, which equals 95.1%. Since the calculated conduit fill of 95.1% exceeds the maximum allowable fill percentage of 40% for 3 or more conductors, we will need to increase the size of the conduit to provide more space for the conductors. A 3-inch RMC conduit has a cross-sectional area of 7.393 square inches. The conduit fill would then be calculated as conduit fill equals total conductor area divided by conduit area multiplied by 100, which equals 3.192 square inches divided by 7.393 square inches multiplied by 100, which equals 43.2%. Since the calculated conduit fill of 43.2% is still greater than the maximum allowable fill percentage of 40%, we would need to increase the conduit size even further, or consider using a larger wire size to reduce the number of conductors. Alternatively, we could consider using a different type of wiring method that allows for a higher conduit fill percentage. For example, cable in free air has no conduit fill limitations. In addition to these factors, it is also important to consider any specific requirements or recommendations from the equipment manufacturer. A manufacturer may specify certain wire sizes, conduit types, or installation methods that are necessary to ensure the safe and reliable operation of their equipment. Always consult the equipment manufacturer's instructions before starting any electrical installation. Finally, remember that electrical work can be dangerous and should only be performed by qualified and experienced individuals. Always follow proper safety procedures and wear appropriate personal protective equipment when working with electricity. Turn off the power to the circuit before starting any work and verify that the circuit is de-energized using a voltage tester. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work for you. They have the knowledge, skills, and experience to ensure that the electrical installation is done safely and correctly. By following these steps and considering all of the relevant factors, you can determine the minimum wire size required for a 277 volts lighting load and ensure that your electrical installation is safe, reliable, and compliant with all applicable codes and standards. Remember to always consult the latest edition of the National Electrical Code and any applicable local codes or regulations before starting any electrical work. And always consult with a qualified electrician or electrical engineer if you are unsure about any aspect of electrical calculations or installations. They can provide expert guidance and ensure that your electrical system is safe, reliable, and compliant with all applicable codes and standards. And remember, safety should always be your top priority when working with electricity.